Imagine humanity finally building a ship fast enough to slip past the edge of the Milky Way, and discovering the universe has laid a trap for us there. A microscopic black hole rhino, smaller than an atom but with the mass of a charging animal, rips straight through the ship's hull, bending metal and space itself, and then vanishes back into the dark as if nothing was ever there. For most of modern astronomy, tiny black holes like that sounded completely impossible. The only black holes anyone seriously talked about were the normal ones born when huge stars die. They burn through their fuel, lose the battle against gravity, and their cores collapse into objects a few times heavier than our sun. Even in the most extreme cases, these stellar black holes start out with masses several times that of the sun, and newborn supermassive black holes in galactic centers can weigh millions or billions of suns. There was no known way for nature to squeeze just a rhino's worth of mass into a black hole, because black holes were only supposed to form from stars, not from something as small as a mountain, an asteroid, or an animal. But as telescopes improved and astronomers started spotting gigantic black holes way earlier in the universe's history than anyone expected, that tidy picture began to crack. If the universe could break the rules to create monsters that were too big too soon, maybe it could also bend them in the opposite direction and create tiny black holes that our current observations are still struggling to catch. Astronomers first realized something was deeply wrong when they started finding black holes that were way too big, way too early in the universe's history. At the hearts of distant young galaxies, they saw monsters millions or even billions of times heavier than our sun already in place just a few 100 million years after the Big Bang, far sooner than standard growth models said was possible. In theory, a black hole born from a dying star should need huge amounts of time to bulk up, slowly feeding on gas and stars while radiation pushes back and limits how fast it can grow. Yet some of these ancient quasars shine so brightly that the black holes powering them must have somehow skipped the slow, patient diet and jumped straight to enormous sizes, forcing scientists to consider a very different kind of origin story. That puzzle opened the door to a radical idea. Maybe some black holes weren't grown at all, but born already huge in the first heartbeat of the universe. And if the cosmos could create giants in an instant, it might also have scattered countless microscopic ones. Tiny, dense landmines throughout the galaxy, still waiting in the dark where our instruments can barely see. To explain how those impossible black holes might actually form, you have to rewind the universe almost all the way back to the beginning. Right after the Big Bang, everything was packed into a hot, violent soup of particles, with some regions a bit denser than others instead of perfectly smooth. In the very densest spots, gravity could have crushed matter directly into black holes, skipping stars completely and creating what scientists call primordial black holes. Because they weren't born from collapsing stars, these primordial black holes weren't locked into the usual mass range of stellar black holes. In theory, they could form at many different sizes, from objects thousands of times heavier than the sun down to versions with far smaller masses. That flexibility turns them into a kind of cosmic wild card. They could have acted as seeds for early galaxies and quasars, or, if they formed in huge numbers at tiny scales, they might still be hiding among the invisible mass that holds galaxies together. In other words, to solve the mystery of black holes that were too big, too early. Many researchers now look back to a universe less than a second old, where density spikes could have punched straight through reality and left behind black holes of almost any size, including the microscopic black hole rhinos your video is teasing. To solve the mystery of those outsized black holes, scientists had to ask what primordial black holes would look like today and whether any of them could still be around. In the standard picture, small black holes should slowly leak energy through a process called Hawking radiation, shrinking over time until they completely vanish, which is why early estimates said the tiniest primordial black holes would have evaporated long ago. More recent work suggests the story might be more complicated at extremely small masses, with some models hinting that the evaporation could slow or leave behind long-lived remnants instead of letting every tiny black hole disappear. That possibility has pushed researchers to design clever new hunts for primordial black holes, watching for brief flashes of Hawking radiation and gamma rays, looking for subtle gravitational lensing effects as invisible masses pass in front of background stars, or using gravitational wave observatories to search for signals from very small black hole populations. If any of those searches finally catch a primordial black hole in the act, it would do more than just prove they exist. It could also reveal whether a hidden swarm of microscopic black holes is helping to make up the dark matter that holds galaxies together. In other words, Confirming even a handful of these ancient objects might tell us that our entire galaxy is threaded with invisible traps left over from the first instant after the Big Bang. Detecting primordial black holes is a tough challenge, but scientists have several promising methods on the table. One exciting approach focuses on Hawking radiation, a phenomenon where black holes emit particles inversely proportional to their size. Smaller black holes radiate more intensely. Recent research proposes using detectors like the Alpha Magnetic Spectrometer aboard the International Space Station to identify sudden spikes in positron particles as a primordial black hole passes near Earth, offering a precise and direct way to spot these elusive objects. Other techniques include searching for gamma-ray bursts from evaporating primordial black holes, gravitational lensing effects as these invisible masses briefly magnify light from stars behind them, and gravitational wave signals from black hole mergers detectable by observatories like LIGO, Virgo, and future detectors such as LISA and the Einstein telescope. These complementary efforts aim to catch primordial black holes across a wide range of masses and behaviors. If these efforts succeed, they might finally prove whether primordial black holes exist today and if they contribute significantly to dark matter. That would mean our galaxy is potentially surrounded by countless tiny black holes, cosmic relics of the universe's first moments, both invisible and incredibly powerful. One of the biggest unsolved riddles in astronomy is dark matter, the invisible stuff that adds extra gravity to galaxies, holding stars in their orbits without glowing, reflecting, or interacting with light in any normal way. It outweighs all the stars, gas, and planets we can see by about 5 to 1, forming massive halos around galaxies like ours, yet no one knows exactly what it is. That's where primordial black holes come back into play as a surprisingly simple explanation. A swarm of tiny ones, each with masses around that of a rhino or small asteroid but packed into proton-sized points, could collectively mimic dark matter's gravitational pull without needing exotic new particles. Unlike larger black holes, these microscopic versions wouldn't disrupt stars noticeably or create obvious lensing patterns in telescopes, letting them hide in plain sight while subtly shaping the galaxy's spin. Recent gravitational wave detections from merging black holes have even fueled the idea, with some masses matching what primordial survivors might look like after billions of years. And if a recent theory holds, their Hawking radiation might stall at tiny sizes, keeping them stable enough to account for most or all of the dark matter today. But proving it means finding direct signs, like unusual gamma bursts or lensing flickers, that could expose our galaxy as a shadowy graveyard of Big Bang relics. If primordial black holes really make up dark matter, what happens when one of these invisible rhino-mass specks brushes past something solid, like a planet, a star, or even our own fragile world? At proton size with the density to warp space itself, it would punch right through without a visible explosion, leaving behind a microscopic tunnel of twisted wreckage where atoms get shredded and gravity plays havoc in a fleeting instant. No fireball, no debris cloud, just a silent scar that might explain odd seismic whispers or unexplained craters if we ever spot the signs. Lucky for us, the odds stay low enough that Earth hasn't been riddled like Swiss cheese yet, and stars keep shining without constant sabotage. But zoom out to galactic scales, and the picture turns eerie. Our solar system could be carving through trillions of these stealthy drifters in the Milky Way's dark matter halo, each one a dormant bomb from the universe's dawn. One wrong pass near a probe or habitat, though, and that future shipwreck from the opening becomes all too real. The chilling kicker? Future voyages beyond the galaxy might force us straight into denser swarms at the edges, turning every leap toward Andromeda into a deadly game of cosmic dodgeball we never saw coming. Until detectors like gamma-ray scopes or lensing surveys nail down the proof, we drift on, surrounded by potential phantoms that could rewrite everything we thought we knew about the dark.